Good afternoon, everyone. I am Bhaskar, and today I'm going to present an energy-efficient medium access control protocol for self-organizing hierarchical ad-hoc networks, SOHAN, that has been developed at WinLab. The outline of today's talk is basically divided into three parts: introduction, prior work, and then the protocol, design, and the simulation and results, and then conclusions and future work. In introduction, I'm going to not going to spend a lot of time on ad-hoc networks and centralized network scenarios and introduction and the overview of the standard IEEE 802.11 MAC. I'm going to say something about SOHAN, the network architecture, and the portions of SOHAN which EEMAP addresses, and for which parts of clusters of it EEMAP is intended for. And then a little bit of prior work as to what are the papers that are already there on and some energy efficient Macs. And in EEMAP, basically it is going to be a protocol, introduction of the protocol, and then design, and the three algorithms, that is the centralized algorithm and two distributed algorithms that constitute this MAC protocol, will be addressed. And simulations and results. The simulations have been carried out using NS tools, and the results will be there, and followed by conclusions in the future. So, going through these, here ad hoc networks, basically the sensor networks EEMAP is going to target are ad hoc networks with highly constrained sensor devices, which are very much power constrained, and they are so they are going to be simple and do not possess high complexity in terms of computation and others. And some of the challenges that these ad hoc networks have is power and throughput and delays. EEMAP is, the main aim of EEMAP is to achieve power savings while considering throughput and delay. SOHAN basically is the TTL hierarchical architecture network, which has the access points, forwarding nodes, and sensor nodes as its network components. Access points are typical 802.11 access points with a wireless interface and a wired interface. Forwarding nodes are multiple interface nodes. They have two wireless interfaces and they are mobile nodes. And sensor nodes are the least complex nodes in this particular network, and they have one wireless interface. They are distributed like this all over the network, that is, the access points they occupy the highest tier, while the forwarding nodes occupy the intermediate tier, and the sensor nodes the lowest tier. And once the discovery and self-organization is done in SOHAN, clusters will be formed wherein a sensor node can talk either to a forwarding node or to an access point. A sensor node cannot talk to another sensor node directly, and then a forwarding node can talk to all the three, that is, any sensor node or another forwarding node or an access point directly, and the access points can talk to both sensor nodes and forwarding nodes in the wireless network and to another access point through the wire. The main portion of this SOHAN architecture that I am going to consider is this, that is a forwarding node cluster. So here, let us assume that this is one of the topologies formed after self-organization and discovery. So here, the EEMAP protocol is applicable for this particular cluster, where S1 acts as the head of the cluster and also a gateway in order to route the data from the sensors to the access point. Some of the characteristic properties are that this is going to act as a head and the gateway, and there is no direct sensor-to-sensor communication, and hence any sensor node, in order to communicate with any other sensor node in the network, should go through either a forwarding node or an access point. This is a basic introduction or an overview of the standard MAC, and this is how the carrier sensing occurs with collision avoidance using RTS-CTS messages. The important fact is that EEMAP is going to address the DCF mode of operation. That is, it is a contention-based algorithm and not contention-free. Now, first of all, why do we need an energy-efficient MAC protocol? There are a couple of reasons. First thing is that the sensor nodes in these typical sensor networks are highly power constrained. We can't afford to lose a lot of power because they might be deployed in places where they cannot be monitored once deployed, and hence we want them to live for longer times and then implement whatever functionality we want them to. So here there are a couple of things that can be identified as sources of power consumption. One of them is communication related. In this case, transmissions, receptions, and forwarding of data. As this basically comes under communication related, but in this case we do not have forwarding because there is no multi-hop communication, and hence it will be concentrated on transmissions and reception. In case of computation, that is basically the processing power that a device uses in order to implement an algorithm or the process the packets received or the packets to be sent. And then the areas where we can concentrate are there's a bursty traffic. This is one of the characteristic properties of most of the typical sensor network applications. That is, usually sensors might be deployed and then they might be expected to send data periodically, and there is no continuous communication. So that is one area where we can try to reduce the consumption of the power. And then retransmissions. So a better way of organizing the communication so that there are not many collisions, and hence less retransmissions will also result in less power consumption. And then control overhead. In order to maintain synchronization or in order to implement an algorithm, some of them might need a lot of control overhead, which is going to again consume more power because of the control packets. And then these are a couple of works done in the field of energy efficient MAC protocols. The main MAC protocol I consider is SMAC, which actually introduced the concept of periodic sleep in ad-hoc networks. And this basically uses this sleep from paper called EEMAP, but there they use two different channels to do that, while these people they did it using the same channel. And in this, the basic mechanism has been modified, and also two more distributed algorithms have been proposed in EEMAP. And then EEMAP is very much similar to SMAC, but they use an adaptive sleep and listen times. That is, in SMAC, while the listen and sleep times are fixed, EEMAP actually makes use of an adaptive schedule. And then a TDMA-based protocol, this considers clusters and also cluster heads, very much similar to SOHAN, where we consider the forwarding node cluster. And then this particular power-saving MAC protocol that has been proposed by Jung and Vaidya, that uses the sleep and listen mode again as an SMAC, but it is going to get rid of certain control packets in the standard IEEE MAC in order to enhance the throughput as well. Now, the main difference between all these protocols and EEMAP is that we do not consider multi-hop communication. Now, the characteristic property of SOHAN, where the sensor nodes do not communicate with another sensor node directly, helps us in the sense the sensor nodes are just one hop away from the forwarding nodes. So this is a one-hop communication, and we avoid any synchronization problems and also multi-hop communication, which might result in delays. Now the protocol. Here the main concept is periodic listen and sleep. But in this case, we see that only the sensor node periodically listens and sleeps, while the forwarding node does not do that. Here we cannot afford the forwarding node to do, because it might be connected to other devices and it might need to do has more functionality than just routing the sensor node packets. So we allow only the sensor nodes to periodically sleep and listen. And one more important factor is that the power capability, the power constraints on the forwarding node are not as much as the sensor node. Then three algorithms constitute EEMAP, one centralized and two distributed algorithms. And then these are certain assumptions that I have assumed regarding the network's characteristics and the traffic model. So here the first thing is, once SOHAN is deployed, the self-organization and discovery process is done, and hence the clusters are formed. Once the clusters are formed, reorganization does not take place frequently. In the sense, once the network is formed, we assume that that is going to be like that for a considerable amount of time, and hence the reorganization process is not frequent. And then the traffic model is bursty, which means the data is expected to be sent only during certain intervals of time. And that is for while they send data for a less amount of time, they are going to remain idle for long periods of time. Protocol design, the main aim is to optimize power consumption, while we consider throughput and delay so that there is not a lot of degradation in throughput, and also we do not allow a lot of delays that might result in a bad performance of the network. And then these things are considered for power reduction. The algorithm that is implemented here is not very complex, and hence processing power is not much. So there we do not actually make the sensors use a lot of power in processing the algorithm and implementing it. Regarding routing, this is actually a characteristic property of SOHAN itself, so sensor nodes do not involve in routing, and hence a computational related power is again decreased here. Control overhead, since we do not have multi-hop communication, there is no problem of synchronization, and hence we do not need any synchronizing packets which add to control overhead. And idle listening, since the traffic is not there all the time, whenever the traffic is not there, the nodes are allowed to sleep, and hence avoid idle listening. In most of the cases, they found that the idle power consumption in a device is very much equal to the receive power consumption. So irrespective of whether a node, sensor node is receiving or receiving data or staying idle, the power consumption is almost the same. So idle listening consumes a lot of energy, and this has been addressed in many energy efficient MAC protocol papers we have done before. Now first going to the centralized algorithm. Here the basic scheme is again periodic listen and sleep. Fn is the one which decides the schedule, that is the sleep and listen times, and then let all the other nodes know about it. So these are certain definitions I am going to use in the future slides, that is sleep time, listen time, slot time, and then the schedule timeout and forwarding node timeout. So when I am actually describing the mechanism, I am going to use these terms and explain you what they mean. So here, first Fn, it decides a sleep time, listen time, and the schedule timeout based on the traffic model and also the topology. And then it is going to send out a schedule packet to all the sensors. Now these sensors, they are going to take this information from the schedule packet, and accordingly they try to listen and sleep. So in this case, the sensor nodes are expected to listen between these times and sleep for this, and again listen, and so this is going to continue. This is periodic. Here there is a possibility that if in case the sensor node has data to send, in spite of the end of the awake period, it is going to send all the data and then go to sleep. So it is going to cut short on its sleep period and not going to affect the throughput load. Now there are
do all the sensor nodes go to sleep at the same time?
Not necessarily. That's what. Here in this case, if you see,
if you have data, then you would not follow your sleep schedule and you continue transmitting your data. But
yes.
Why do you have the sensor nodes original sleep schedules aligned?
This one?
Yeah, SN1 and SN2, they can have awake and sleep in alternate manner.
Yeah, that becomes a TDMS sort of a scheme, which is not. This is basically contention based, and this is not a TDMS scheme. If you actually defer this particular data to the place where after SN1 sends, it is basically time slotting. So you are giving time slots.
You need not have, orthogonal slots. They can be, slightly offset.
Yes, actually that is the distributed algorithm. That is going to be the next algorithm I'm going to talk about. So in this case, this is a simple implementation of sleep fake. So here that is going to be the case, but there might be a case when a sensor node joins this particular cluster after the initial topology is already formed, where we come up with two cases. The first one is the SN joining when the other nodes are awake. So in this case, here the sensor node joins, the schedule packet that is being sent to this particular sensor node is going to be a bit different. The slot time is basically a sum of the awake time and the sleep time, and that is always fixed. So here sleep time is fixed, then the slot time is fixed, and the listen time will vary based on when the node joins. So initially when this node joined the cluster at this point of time, this particular listen time is different, say it is TL1.
How does, when the node joins, how does it know what this awake time is? How does he get that?
Yeah,
prime?
Forwarding node is going to send the schedule packet to the unicaster, to the forwarding node that joined later.
There's still no one associated with this one node shift, so one node we have responses,
Yes. So in this case, in the first slot, it is going to adjust itself so that it is going to listen for this amount of time, provided it can send all the data it has during that time. and then going to sleep for this. For the next consecutive slot, it has to calculate the result time that is there for all the other nodes. So it is going to calculate that like this, because the slot and the sleep times are always the same. The difference is going to give the result time for all the other nodes. So after this particular cycle, from here onwards, it is going to follow the same cycle as the other nodes.
Question. So how does the forwarding node even decide the schedule based upon what?
It's the traffic model and topology. So for example, say there are 5 sensor nodes in its cluster, and each of the sensor nodes is expected to send data for some 512 byte packets, 10 packets of 512 byte size each. So it is going to calculate the time that is required for all the sensor nodes to send the time and add a little amount of buffer time so that the content that is going to be accounted for the contention, and then it is going to decide.
But didn't you say that the traffic is not worth it? That is a lot of time cycle, then suddenly it's a lot of traffic.
No.
How do you?
No, it's bursty in the sense it's a bit deterministic. That is for sure. Let us consider a scenario where we have a couple of sensors deployed in this room, and then we have a forwarding node.
So how do you handle those situations where, let's say, if the temperature reading is below a certain level, you don't send. If the temperature reading is above a certain level, you have to send very frequently.
Yeah.
That way, how do you decide the schedule?
That adaptability is not there in this particular algorithm, but in the later algorithms, those packets will be buffered. But that will again add to delays. So we can come out with another algorithm which will actually adapt itself to those kind of environments. So in case sensor node joins this particular cluster during when other nodes are sleeping, this is going to be the case where the sensor node is going to be awake during this time and also during the sleep of the other nodes, and it is going to synchronize with the rest of the nodes from the next cycle, and that is obviously what is going to happen again. So here one thing is, whenever a sensor node joins or the cluster is formed, initially all the sensors will be in the awake mode. They are not going to sleep. They are going to sleep only after their awake is over. And FN timeout is one more parameter which is used in case a sensor node does not receive a scheduled packet from the forwarding node. So in case the sensor node does not receive a scheduled packet from the forwarding node, it is going to wait for the FN timeout period, and then it is going to probe the forwarding node. So once again, it is going to be similar to this case, where say this is the delay, where this might be actually the delay in which this particular sensor node receives a scheduled packet from the forwarding node after being probed. The distributed algorithm. One main problem with the centralized algorithm is that all the sensor nodes content for the medium during the given amount of time, which will lead in a degradation of the throughput, and hence we can try to actually design.
So, but in centralized algorithm you have to control, right? You can always find that.
Yes. Yes. That is what actually distributed algorithm here is not really completely distributed. Rather, this is centralized decision making. No, actually centralized intelligence with distributed decision making. So even here the forwarding node is going to actually give a schedule. But the time when the sensor nodes are going to send the data, sensor nodes themselves will decide it. So it is not completely distributed. This has a centralized mechanism actually. So in this, most of the definitions are the same except for the active window and then wake up time. So in this case, again, there will be a scheduled packet that will be sent by the forwarding node to the sensor nodes. Here, instead of this particular listen time, it is going to have something called an active window. And these sensor nodes are expected to generate a random number within this active window size. And at that particular time, they will start sending their data. So here, all the sensors are not sending data at the same time. So in this case, the contention is reduced.
So why even try to do this at all? Why not just go for a
centralized TDMA scheme, if you're going to announce schedules.
Yes, if you go for a TDMA scheme, the adaptability will be less. In the sense, if you want to change the size of the slots on the fly, it will be difficult when compared to this particular scheme. Career sensing, you can very easily change the schedules and also these active window sleep times on the fly. It is a bit complicated in case of TDMA. But sure, TDMA is definitely one of the options, and you can actually design another MAC protocol based on TDMA schemes.
Well, I guess you can extend the question and say, okay, so don't assign it on slot, fixed slot. Have it variable slot, but have the controller decide the slot boundary.
Okay, once again, it's actually, this is going to result in delays. So one thing is that, say if you are actually going to fix the slots and then make the sensor nodes decide on the slots, first of all, this particular control package, it is going to be more. That is going to have more fields in it. It is going to increase control overhead. This control overhead results in more power consumption. We are trying to make this as simple as possible. One more thing is the sensors need to do a lot of computation in order to actually go through the slots and then choose one time. Here, I try to make this particular mechanism as simple as possible. But yes, that is possible. You can do that.
I think it's like
It's a trade-off.
sensor slot. I mean, the sensor node did not transfer in a slot, but forwarding node doesn't know that. Even if it assigns a slot in TDMA, that's not a good option.
I'm sorry?
If you do TDMA,
Yeah.
so
As I told you, TDMA, it is not very easy to change the active window size. This active window size and sleep time are not fixed throughout. They will be changed periodically. So in TDMA based scheme, it is not so easy to change this on the fly.
yeah, that's right. I was saying the additional disadvantage can be like the forwarding node doesn't know when the sensors will transmit. So even if it assigns a slot,
Right.
that might get wasted. Whereas in this method, and depending on
Yeah, the data, these sensors are going to send the data.
So we are not doing carrier sensing here?
Yeah.
Yeah.
They'll be doing the carrier sensing from this point, whenever they want to send the data. Initially, in this active window, though the random number is selected and it is here, it is going to stay awake till this point, but from the next active window onwards, it is going to sleep throughout this time and start wake up only when it has that random number, the timer expires, and it is going to wake up and send the data and sleep.
So based on the traffic profile, that may turn out to be a constant activity for all the, if the traffic is such that basically we need to send something all the time. So it's going to basically boil down to a trivial case.
Yes.
Everybody's sending all the time.
Yes. In this case, this basically has this particular distributed mechanism has a feedback mechanism implemented in it. So in the previous case, if you see the random numbers are being generated, and there is a possibility that all the sensors actually choose the same random number or with a very less difference, and hence again there will be a lot of contention in data transmission. So in this case, what happens is the sensor nodes are going to choose random number in the first active window. They are going to send their data, sleep after that, and they will wake up exactly at the end of the sleep period. They are going to generate a new random number now. In the first case, they are going to record the energy consumed in this first active window, and then here they are going to repeat the same procedure. They are going to record the energies consumed during this active window. Now they will compare these two energy levels, and whichever is lesser, they are going to choose the corresponding random number and will use that particular random number for the next consecutive communication. So in this case, there is a possibility that each of these sensor nodes, they are trying to minimize on their energy consumption. So this might result in a better scheme. But again, there is one problem where, since this is being decided on a distributed manner, this particular sensor node in the first case might have actually used less energy. This might have used less energy in the second case, but if you look it together, this and this put together might consume more energy. But when I actually simulated and got the results in almost all the cases, either the performance of this was better than the previous distributed algorithm, or they were same, but it was never worse.
One question. You said that the sensor nodes are performing carrier sensing, right?
Yes.
And SM1 and SM2 are sharing the medium. So
Yes.
how can this simultaneously implement?
Oh, okay. This is not exactly the timing diagram. This is to just say that the sensor node tries to send the data at this time, and the sensor node 1 tries to send the data. But definitely you'll have all the DIFS, SIFS, everything will be there. This is, you can assume that this is the listen period where they are trying to communicate, that's all. So this is basically what was explained before. So this is going to happen, and these energies are going to be noted, and then the random number with respect to the least energy, less energy is going to be taken into consideration, and that will be used for the next transcatal communication. The simulation parameters are used for energy consumption, average entry delay, and throughput. And then these are a couple of modifications that were made to the network simulator. These are the node specifications. The radio range of the node was equal to 250 meters, and then these power consumption values have been taken from SMAC. So this is basically the topology. A forwarding node at the center of a 250 meter range, so 500 by 500 square, and all the sensor nodes are distributed at random within this particular 250 meter circle, because they should be one hop away from the forwarding node, and hence directly in communication with the forwarding node. And the bandwidth used was 1 Mbps, CDR and exponential traffic in order to introduce bursted traffic. So CDR is more deterministic, where I actually have traffic at regular intervals, while exponential traffic gives random bursted traffic. So here the packets are going to be buffered. And the packet sizes for various simulations are those. So here if you see, this is a comparison between the standard IEEE 802.11 MAC and then the sensor MAC and the 3 algorithms of EEMAP. So here we see that there is a considerable savings in energy when compared to these two. And these 3 algorithms, they are similar, or they are actually fall in the same region, because there is not much of a difference between these 2 distributed algorithms and also the other one.
Question?
Yeah.
Why is the performance so bad?
I simply used their protocol, I implemented that. So there might be a case. Actually here the x-axis represents the interval time. That is, 1 means there is here the burst time is 1 second. So that is 1 second where the burst and 1 second sleep. Similarly 5 and 10 means 1 second burst and 10 second sleep. And also the nodes are distributed randomly. So in this case, if you know how SMAC performs, they are going to at random choose one node and it is going to send the schedule. So there is a possibility that there is a border node problem in this. So there might be a possibility that there are more number of border nodes which are actually consuming up more, they are listening for more amount of time and also consuming up more energy. And moreover, this is completely distributed. So there are sync packets in order to synchronize all the nodes, and then there's a lot of control overhead.
So what is the duty cycle you choose?
Duty cycle varies from 1 to 10.
What was the direction of the CDR traffic? What's your direction?
Oh, it's going upwards from the sensors
From someone
to the forwarding node, yes.
Only one direction?
Yes, only one direction.
One more question. So if the duty cycle, let's say at the extreme, you're saying 18% seconds, and
Yes.
you're up for 1 second.
Yes.
Then consumption should be 110. That's much less.
SMAC?
Yes.
Okay.
Should that simple mathematics will hold, right? Let's just keep it for 1 second.
Yes.
So 10 seconds will take you for 1 second.
Yes.
So you're consuming 1/11th of what you should be consuming when everybody does.
This particular thing, it actually has random topology that is being changed. Okay, you it is for this particular simulation. Okay. I really do not know the performance, how it is being implemented in NS2. So I simply used SMAC and then computed the energy values and then I plotted. So I'm not really sure if it has been, first of all, if it was implemented in the proper manner. So I simply used it. So here this is the energy consumption with respect to the number of nodes, sensor nodes in the cluster. So there is one forwarding node, in addition to that one sensor, 2, and it goes up to 5 sensor nodes. And this is a performance comparison between IEEE MAC, SMAC, and then the centralized algorithm. And this is the comparison between the 3 algorithms of EEMAP. And here we see that the centralized algorithm, it consumes more energy, and distributed, it is not actually completely distributed. The intelligence is centralized. but the way in which they decide their times, wake-up times is distributed, and then they perform better and they consume less energy. This is because we are reducing on the contention, and also because of that we are reducing collision-centric transmissions of packets. And here, this is a delay measurement. This is basically percentage of energy savings when compared to the standard IEEE MAC, and this is for the centralized algorithm for 1 sensor node, 5 sensor nodes, and 10 sensor nodes in the network and the cluster. And this is, we can see that till we achieve at least 50% of power savings, the delay is not shooting up. In the sense, the delay is pretty much consistent, and hence there is not much trade-off in terms of delay. This is a comparison between the 3 algorithms of EEMAP and the IEEE MAC. So the delay is definitely more than standard MAC. Here this is a throughput comparison. The performance of the centralized algorithm in terms of throughput is also bad when compared to both the distributed cases and the standard IEEE MAC. So here again, once again, the trade-off is between the throughput and energy savings, and also delay and energy savings. This is throughput comparison with for different packet sizes between the 3 algorithms of EEMAP and standard IEEE MAC. So here this can be actually used like a knob, in the sense we can try to adjust the power savings, and hence we can gain on throughput and also delays. And if you want more energy savings, and we can actually, if we can tolerate so much throughput degradation and delays, then we can try to consume less energy and hence try to optimize it in terms of energy. So the parameters can be changed, and hence performance variation can be observed.
Bhaskar, in some of these curves, you need to identify the key design parameters for your scheme.
Okay.
Because there's not, I mean, the way it's plotted makes it seem like it's a universal result, but this is for a certain activity factor.
Yes.
And traffic model and
Yes.
delay and those on-off times
Yes.
are key parameters.
Right. In this case, the burst time was fixed at 1 second, but the idle time was changed, and hence there is a change in energy consumption. And in this case, the energy savings were around 60%. So that was I think, I don't exactly remember the burst and idle times. And these are the delays plotted for that particular traffic model. And in this case, the bandwidth is saturated. In the sense, the data flowing through the cluster is more than 1 Mbps, which is the bandwidth. In both the cases, that is the case. So an energy efficient MAC protocol has been proposed for SOHAN, basically the hierarchical ad-hoc networks. And then certain characteristics of the ad-hoc networks, self-organizing hierarchical ad-hoc networks, have been used in order to conserve energy, and some of them have been the sensor nodes not involved in routing, which is going to reduce considerable computation energy at the sensor nodes, and also the forwarding node, which is more hardware, which has more hardware capabilities, which can actually control the sensor nodes within the cluster, and that is going to help us in many ways. And then the centralized algorithm and the distributed algorithms, they have been compared with MAC and SMAC. The performance with MAC is a fair performance, but here SMAC, it has been implemented as the way it comes with the NS2 simulator. So, and then the feedback mechanism in the distributed algorithm too, it helps to improve the performance when compared to the first distributed algorithm. And then the sensor network, the sensor node complexity has not been increased to a very great extent, because the algorithm here proposed is very simple, and it does not need a lot of processing power in order to implement that as per the algorithm. The future is that the forwarding node actually can be used in order to have more intelligence, and hence decide the sleep times, present times, and other parameters, not only based on the topology and the traffic model, but also parameters like mobility. And also it should be robust in terms of reorganization, because here one assumption is that the sensor network is not going to organize itself very frequently. but even that can be handled if there is more complexity in implemented in the forwarding mode. And this particular centralized algorithm, at the return time in this and the active windows in the distributed algorithms, they can be chosen in a better way, wherein they actually try to reduce, in this case, they try to reduce the contention and also the energy consumption to a greater extent than what we have seen here. And then choosing the number of active windows before deciding which particular awake time this node should use will definitely affect this, because in this case I'm considering only 2 active windows, after which the sensor node is going to decide on wake up time to send this data. But this can be increased, and it can actually be chosen based on other parameters of the cluster, and that might yield to better conserve the energy than now. So these are a couple of things that are open that can be actually worked on in the future.